Section 3.3, Complex Zeros and the Fundamental Theorem of Algebra. So first let's talk about complex numbers. And the deal is that the set of complex numbers can be thought of as the largest set. Now when I say the largest set, I mean it's the largest set of numbers because it really contains all of the numbers that we've talked about in our classes. And so it's going to contain the reals, the rationals, the irrationals, and the integers. And just to throw something at you, some notation you may see. Sometimes the complex numbers are referred to with a double script C. Sometimes the reals are referred to as this R. Sometimes the rationals are referred to as the set Q. And then the integers are sometimes referred to as the set Z. Now irrationals don't get their own symbol. Usually they're just called the reals minus the rationals. And so just for some notation, the truth is the complex numbers will contain, so everything in the reals is inside the complex numbers. The other thing is the rationals are part of the reals, and the integers are all rationals. And so some of these things are nested. But then the reals are made up by the rationals and the irrationals. Notation and just some facts here. This symbol means contains. That's one way to think of that symbol. Alright, well then we get this thing called the fundamental theorem of algebra. And the deal is that the fundamental theorem of algebra says that every polynomial function of degree n being greater than or equal to 1 with complex coefficients has at least one complex root. Well, what does that really mean? What it really means is that for every polynomial function of degree 1 or larger, then we can factor it into the same number of linear factors as the degree. Now, it's not necessarily true that those factors are unique, but each one of the CIs that we find are going to be zeros of f of x. And so specifically, we'll see this, which we've talked about before, that is some leading coefficient times x minus the 0 c1 times x minus the 0 c2 times all the x minus zeros. And so that's the way that we can construct polynomials like we've been doing already. And so once again, just to review, the deal is that if we are reverse engineering a polynomial given at zeros, remember that if we know the zeros, specifically the roots are 2, 3, and negative 4, remember that given some 0, c, then the factor will be of the form x minus c. And so given the 0, we get the factor. And so if we were trying to find a cubic polynomial with roots 2, 3, and negative 4, that is any coefficient multiplied times x minus 2, x minus 3, and x minus minus 4. Now, this a sub n really could be any real number. If it has complex coefficients, technically it could be any complex number. But in most cases, we're going to limit ourselves to real coefficients as opposed to complex coefficients. And so then what can we do? We can clean it up a little bit, and then if we want to multiply this all out, you could. But also, in general, we're just going to assume that that coefficient a sub n is 1, just because it's the easiest case. If somebody tells you that it has a different leading coefficient, then you change that leading coefficient. Now, everything that we've dealt with up to this point has really usually been real zeros, and usually rational zeros. We might have seen an irrational 0 or 2, but what matters is that complex zeros and irrational zeros are always going to come in pairs. Specifically, we call those conjugate pairs. And so the deal is that if we know a polynomial function has a complex 0, where c is equal to a plus bi, then the complex conjugate is just going to be take and change the middle sign, and so its complex conjugate c bar is a minus bi. And so, in general, if we ever have a complex 0, then its complex conjugate pair also is a 0. This also means that if a polynomial is of odd degree, that there must be at least one real 0. So now we want to find a polynomial of lowest degree with rational coefficients. The rational coefficients is technically the thing that forces the complex conjugate pairs and the irrational conjugate pairs. So let's think about this a moment. If we have a 0, that's 5i. And we have a 0, that's root 3. If the polynomial has rational coefficients, then I know that these things have to have the conjugate pairs occurring. That is, 5i occurs, and then the sign in front of the I part has to change, and so I also get negative 5i. Well, with the radicals, with root 3, if root 3 occurs, then negative root 3 must also occur if we know that we have rational coefficients. So that means our zeros are 5i, negative 5i, root 3, and negative root 3. This has to be the case because of the rational coefficients statement. And so then to make this polynomial, that is x minus 5i times x minus minus 5i times x minus root 3 times x minus minus root 3. And so then we can multiply these things out to simplify. X minus 5i times x plus 5i. Clean that up. This is a difference of squares, so when I multiply it will be easy. And then also x minus root 3 times x plus root 3. This is also a difference of squares. And so x minus 5i times x plus 5i, you can FOIL it and then see that the inner and outer terms cancel, but we can jump directly to the fact that this is really x squared plus 25 times x minus root 3 times x plus root 3. The same thing happens. You can multiply it out via FOIL and you'll see that the inner and the outer terms cancel, but you could jump directly to the fact that this is x squared minus square root of 3 squared, or 3. And then we can multiply this together. That's going to give us x to the fourth minus 3x squared plus 25x minus 75. That is x to the fourth plus 22x squared minus 75. So this is the polynomial of lowest degree with rational coefficients that has the zeros 5i and root 3 in it. Now we want to find a polynomial of lowest degree with rational coefficients that has the zeros at 4, 1 plus I. Alright, so let's think about this a moment. If it has rational coefficients, that means complex numbers have to have a conjugate pair, and irrational numbers have to have a conjugate pair. We don't see any radicals, so there's no irrationals, but we do have a complex number that is 1 plus I. Because we have rational coefficients, 1 plus I occurring forces its conjugate pair 1 minus I to occur. And then the real 0, 4, well, there's no weird issues that occur with just integers. And so we don't have to worry about it. It's perfectly fine. Well, that means that our polynomial is going to be x minus 1 plus I times x minus 1 minus I times x minus 4. Then if we need to simplify this, we need to multiply these together. So let's be careful here. I'm going to take the conjugate pair factors and multiply them together first because that's going to make life better. We can leave it like this, or you could work with the trinomial forms. That would be x minus 1 minus I times x minus 1 plus I, all times x minus 4. Then I'm going to multiply these two. X times x is x squared. X times negative 1 is negative x. X times I is plus xi. X, then we're done with the x. Then negative 1 times x is negative x. Negative 1 times negative 1 is positive 1. Negative 1 times I is negative I. Then negative I times x is negative xi. Negative I times negative 1 is positive I. Negative I times positive I is negative I squared, all times x minus 4. Then some notes. Of course, I squared becomes negative 1, and so this is minus minus 1, or plus 1. And then we have x squared is its only like term. Negative x is negative 2x. Then plus xi minus xi, that gives us 0. Minus I plus I, that gives us 0. Then I have plus 1 minus minus 1, which is 1 plus 1, or plus 2, times x minus 4. Then to put that in simplest form, continue to multiply. X times x is, that's x squared. X times x squared is x cubed. X times negative 2x is negative 2x squared. X times 2 is plus 2x. Negative 4 times x squared is minus 4x squared. Minus 4 times negative 2x is negative positive 8x. Negative 4 times 2 is negative 8. Then we get that this is x cubed minus, so minus 2x minus 4x, that's minus 6x squared. Then 2x plus 8x is plus 10x minus 8. And so I claim that this is the polynomial with lowest degree that has the zeros 4 and 1 plus I in it. And it does have rational coefficients, which is what's forced the conjugate pairs to occur. So now we want to find the zeros of the polynomials, and then we want to write this in its factored form. So first things first, if you can group polynomials, if it's a polynomial with 4 terms, group it, try it. If it works, you make your life easier. If you can factor out a greatest common factor, always factor out a greatest common factor. All of our old factoring methods still work. But the moment that we recognize that our old factoring methods aren't actually going to work here, then we need to use our new factoring methods. And the first tool that we have is the rational roots theorem. And so the rational roots theorem, remember, gives us possible zeros, specifically possible rational zeros. And so we just need to make that list. But remember, the possible rational zeros, the rational root tests, is going to be the factors of the constant over the factors of the leading coefficient. And so we have 26 is our constant, we have 1 is our leading coefficient, and so our factors are going to look like this. Well, over 1 because the leading coefficient is 1. But then we got to think about all the numbers that can multiply together with other things to get 26, but we're looking for whole numbers. So 1 times 26, 1 and 26, and then also we have 2 times 13, and then we have to do the plus and minus of every one of these. And so that is going to give us our list of possible rational zeros. Specifically, we'll have positive 1, negative 1, positive 2, negative 2, positive 13, negative 13, positive 26, negative 26. Now once again, this is not necessarily the zeros, but I claim that if we have rational zeros, I guarantee they'll come from that list. Which then means if you want, you can do one of two things. You can either do the synthetic division, which is what I'm going to do, to check and see if we have zeros, or you could plug in each one of these values into the polynomial until we find zeros. And the moment that you find a zero, you could actually factor it using synthetic division, because we have a linear factor here, and you can break it up further. So let's run through this. Well, I'm going to use synthetic division, and so my coefficients are 1, negative 8, positive 25, negative 26, and then I'm going to use the zeros to test and see if they are zeros of the polynomial. So, for the sake of practice, let's start with positive 1. Let's see if this works. Well, remember our algorithm. I'm going to go ahead and save us a moment here. Bring down your first coefficient always. Alright, then 1 times 1 is 1. Add down, that's negative 7. 1 times negative 7 is negative 7. Add down, that's going to be positive 18. 1 times 18 is 18. Negative 26 plus 18, notice, is not 0. And the moment that I see that this thing is not 0, there's a remainder, and if there's a remainder, that's not a divisor, which means that this is not a 0. Now you could keep going through the list, but to save us a little bit of time, I'm going to jump to what I know to be one of the zeros, and that is 2. So let's check. 2. 2 times 1 is 2. Negative 8 plus 2 is negative 6. Negative 6 times 2 is negative 12. Negative 12 plus 25 is positive 13. 2 times 13 is 26. Add down. The remainder is 0, which I know now means that this thing will factor. Specifically, it factors as x minus that 0, 2, and also 2 is one of our zeros. X minus 2 times, these are the coefficients of 1 degree less, that is 1 times x squared, then negative 6x plus 13. At this point, there's no more reason to work with this initial polynomial, because if we factor this correctly, which I claim we have so far, you have a smaller part that you can work with easier. Now at this point, if this trinomial would factor, factor it. If this trinomial doesn't factor, then we should probably move on and go try the quadratic formula. I'll save us a little bit of time, and I'll tell you that this thing does not factor, and so we do need to use the quadratic formula. Negative b plus or minus the square root, b squared minus 4 times a times c, all over 2a. And so that's going to be negative negative 6 plus or minus the square root, negative 6 squared, minus 4 times 1 times 13, all over 2 times 1. Then we get that this is positive 6 plus or minus the square root of 36 minus 52, all divided by 2. That then gives us 6 plus or minus the square root of negative 16, all divided by 2, which then gives us 6 plus or minus 4i, all divided by 2, which then reduces to 3 plus or minus 2i. So now I know that all of my zeros, all of them, rationals and complex, and irrationals, are 2, 3 plus 2i, and 3 minus 2i. So we found all the zeros. That was one goal. The next goal is to factor it completely into linear factors. And so if we want linear factors, that's going to be x minus 2 times x minus 3 plus 2i times x minus 3 minus 2i. And so that's the completely factored form into linear factors. And then we also found the zeros. Now we want to do the same thing. Once again, if you can factor this via our old methods, go for it. But I don't see any way that that's going to work. And so the first thing we need to do is use our rational root test to come up with possible rational zeros to test. So remember, the rational root test, or the possible rational zeros, is going to be the factors of the constant over the factors of the leading coefficient. So we see that our leading coefficient is 1, lucky us, so that's over 1. And then the factors of 175, but the factors of 175 are all the numbers that multiply together to give us 175. That's 1 and 175, 5 and 35, and 7 and 25. So 1, 5, 7, 25, 35, 175. And once again, the plus and the minus of each one. And so our possible rational zeros, the rational root test, are positive and negative 1, positive and negative 5, positive and negative 7, positive and negative 25, positive and negative 35, positive and negative 175. At this point, just start somewhere. So let's start with the 1. Let's see if we get lucky. So if I start with 1, use the synthetic division. My coefficients are 1, 6, 18, 150, negative 175, and 1, bring down the 1. 1 times 1 is 1, 6 plus 1 is 7, 7 times 1 is 7, 7 plus 18 is 25, 1 times 25 is 25, 150 times 25 is 175, 175 times 1 is 175, 175 minus 175 is 0. We have a 0 remainder. So that means that this thing will factor. So we can go ahead and factor it a little bit if we want. We know that it's going to have the linear factor x minus 1 times 1 degree less, that is x cubed, plus 7x squared, plus 25x, plus 175. So we've already gotten to a better form. Now at this point, I claim now we really just need to factor this thing some more. But notice that the constant is the same constant we had previously, which means that our possible rational zeros list is going to be the same. Now, side note, we already found that 1 is a 0. Technically, it's possible that 1 shows up again. So be aware that that is a possibility. But I already know some stuff, so I'm going to tell us that it's not another 0, but it could be. So there's nothing wrong with testing it again. You could also try negative 1, 5, negative 5, so on and so forth. So for the sake of practice, I'm going to erase the synthetic division, and then I'm going to write it with the new smaller polynomial. Because once you've factored it some, there's no reason to have to work with the larger polynomial anymore. We now know that we're really just trying to factor this thing. And so my new polynomial that I'm going to divide is x cubed plus 7x squared plus 25 plus 175. But once again, my list ends up being the same of possible rational zeros from that polynomial. And so why don't we try 5 for the sake of it, just for some practice. So bring down our leading coefficient. 1, 5 times 1 is 5, 5 plus 7 is 12, 12 times 5 is 60, 60 plus 25 is 85, 85 times 5 is 425. At this point I'm going to stop because I realize that my remainder will not be 0, and therefore 5 is not a 0. And so I'm going to mark it out. So now I'm going to jump around a little bit, and I'm going to try negative 7. You may not pick the right one the first time. You may have to jump around a little bit. Sometimes that's what happens. Once again, if you would rather, you could plug in negative 7 just into this polynomial and see if you get 0. You could do this with any of these values. If it gives you 0, then it's a 0, and then you would need to just factor it further. So negative 7 times 1 is negative 7. That gives us 0. Negative 7 times 0 is 0. That gives us 25. Negative 7 times 25 gives us negative 175. 175 minus 175 is 0. My remainder is 0. I now know that negative 7 is a 0. And I know that this thing now factors as, it's already got that x minus 1 factor, but now I know it's got a factor of x minus minus 7 times what's left here. Well, this 1 goes 1 degree less, so this is going to be x squared. And then this 0 is the coefficient of x plus 25. Now at this point, we could clean it up some. That is x minus 1 times x plus 7 times x squared plus 25. Now I see it's a quadratic, and if you want to use the quadratic formula, that's okay, but I'm going to save myself some time, and I'm just going to take that and use the square root property. X squared plus 25 is equal to 0. Minus 25 minus 25, that is x squared is equal to negative 25. Then I take the square root of both sides. When you take the square root of a square, you get plus and minus. And so this is then going to be x is equal to plus and minus the square root of negative 25, which is really 5i. So now I have all of my zeros. All of them. They are 1, negative 7, positive 5i, negative 5i. Notice that we didn't have to do anything weird because the complex conjugate pairs just pop out of our quadratic. So then if I want this in complete linear factors, that is x minus 1 times x plus 7 times x minus 5i times x minus minus 5i, which is really x plus 5i. And so now I have it completely factored into linear factors, and I found all the zeros.